x1 squared plus, we'll call it c1. And now we'll take the integral of that again. Yeah, equals dv. Oh, not dv, just v. V is equal to, what is it? 625 divided by 3 times x1 to the third plus c1 x1 plus, we'll call it c2. Right? Good. Now for this side, let's do the same thing. So EI times dV dx is equal to, what is it? It's 375 times x2 squared plus, we'll call it c3. Now let's integrate it again. We get E times I times V is equal to, I think it's 125 times x squared to the third plus c3 x2 plus, we'll call it x4. Cool. Now we could, we could take this equation, and if we wanted to know the deflection at c, right, all we had to do is plug in x1 at 3, which is 3 feet. So we plug that in there, and we could get, and divided by E9, we get the deflection, right? But we don't know what C1 and C2 is, and for that matter, we don't know what C3 is and C4 is. So we're not quite done yet solving those equations. We need to know what the C's mean before we can really solve anything. So let's see if we can figure that out. All right. And then I wish I had more room for writing. Okay. Hopefully you can see this. I'm going to write down, if you want to figure out what those C's are, you need to find key points where you can solve for them. And the key points or key things that we can look at is we can look at A. What's happening at A? Well, we know that there's going to be no movement at A. It's stuck there because of that support. So we know that when x1 is equal to 0, then the deflection is equal to 0. So V is equal to 0. So let's write that down. When x1 is equal to 0, then we'll call it deflection 1 is equal to 0 as well. And that's the same for B2, right? So when x2 is equal to 0, so when that x value is equal to 0, then that second equation, V2, that one over there, is also equal to 0. Now when we plug those in, we find that both, and so this is the deflection, this one right here, underlined, and this one right here, are deflection equations. They're going to equal 0 when the x is equal to 0, which means C2 and C4, at least for this beam, they're both equal to 0. So let's write that down up here. We're going to make a small box, C1, C2, C3, C4. C1, we don't know what C1 is equal to, but we know that C2 is equal to 0, we know that C4 is equal to 0. Just from these two things. That's awesome, that just cuts us down to 2. So let's actually erase those from our equations. Well, no, I'm going to leave up there so you can remember them. Okay, so we need 2 more equations, right, to solve for these last 2. 4 equations for unknown, so now we just have 2 left, so we need 2 more equations. So let's look at here. What's happening here at C? Well, we know that the deflection of the first equation, right here, at C, deflection of the first equation has to equal the deflection at the second equation at that point. So we know that they have to be equal. So V1 equals V2 when, I don't know, x1 equals, what is it, 3, and x2 equals 5. Good. So that gives us an equation. We can put these 2 equations equal to each other, and that'll help. We also know that the slope there is going to be the same. Well, since we're actually taking this equation, we're going backwards. So when you put them equal to each other, they should be opposite. But the deflection there is going to be the same for this side and that side. So what I'm going to do is I'm going to say that dv1 equals dx, or dv dx, dv1 over dx is equal to negative, and that's because this equation is going backwards, remember, for the second one? Negative dv2 over dx when x1 equals 3 and x2 equals 5. Okay, now you can make those equations. This one up here is our slope equation, as well as this one. So you can put those two equal to each other for that last point, that last equation. And when you do that, don't forget that when you're plugging your x's in, you really, really, really want them in base units. You do not want to plug in your x's as 3 feet and 5 feet. You want them, so I guess this and this aren't really accurate, because I have them as x1 equals 3, when x1 should actually equal 36 right here, and x2 equals 60. They have to be in base units. Do not forget that, or else you'll get something weird. And that's just never cool, right? Right. And one of the main reasons we want it in base units is because the I and the E over here in the equations are in base units. You are given the modulus of elasticity in base units, and so you need everything else to be in base units in order to use that. Okay, so when I've done that, just so you can see what I'm talking about, I'm going to, man, I wish I had more room. I'm going to erase these. I'm pretty sure you know these. And I'm going to write down, and you guys know those, right? Yeah. No, I'm going to leave them. Okay, so for this one, for the first one, we put, what is it? The v1 equal to 0, so we take this equation, put it equal to 0 when x1 equals 0, and that's how we found that c2 and c4 are 0, same with that one. And for these last two, I'm going to take the deflection, this equation. So I'm going to say v1, and I'm going to divide it by IE. Remember, move that over so you get v1 by itself is equal to v2, well, here I'm going to do it like this. v times, when x1 equals 3, which is 36, is equal to v2 when x equals 60. And d v dt, or not t, x1 when x equals, what is it, 36 still? It's equal to dv2 dx when x equals 60. Cool. You can then solve for c using whatever method you like. I did it using Excel. And when I did it, I found that c1 is equal to negative 117 with 4 zeros. 1, 2, 3, 4. And that c3 is equal to negative 9 with 4 fours. Now I'm actually super confident in these numbers because I went through it like 3 times to make sure I got the right ones and used several different methods of doing this. And yeah, I can now take those and plug these into these equations and then solve for our v. Do not forget to divide whatever you get for this by the I and E so you get your deflection. And once I have done that, I found that the deflection at C at that point is equal to 0.10474 inches. Yep, and that's a pretty cool concept to remember. Just remember how to use those different methods. Don't forget to look for key points and ask yourself, hey, is the deflection equal to 0 at any point? Do I know this for certain? Perhaps you could even look for, where do I know the slope is 0? We don't actually know where the slope is 0 on this one, but you can ask yourself that. Where is the deflection of two different equations equal to each other? Where is the slope equal to each other? Whereas, just ask yourself where those points are so you can use that knowledge to solve out how this beam is going to react. And yeah, that's how you deal with a deflection in beams mathematically.